Hello everyone, welcome to this lecture in the Decision Trees from Scratch series. Today we have a very important topic to cover, which is usually not covered in too many decision tree lectures. Today we are going to talk about pruning, and we are going to talk about pruning in decision trees. Especially, we are going to look at classification trees and understand pruning from scratch. If you have been following this series, in the previous lectures, we have built an entire classification tree from scratch. However, if you have not seen the previous lectures, it's totally fine. I've designed this lecture in such a way that even people who are coming new will completely understand this lecture and get a flavor of how we usually do things in this series, which is completely in a hands on manner. And I write and show everything to you on this whiteboard. So let's get started. The problem which we have been considering for the past many lectures now, is that this is the training data set which we have. So I'm going to call it training. This is the training data set which we have. We have essentially collected information from seven different people, and we have first asked them, do they love movies or not? That's the first question. Then we have asked them, do they love cartoons or not? Then we have also collected their age. And then finally, we have asked them, do they love Batman or not? So the goal is that based on this training data, when any new person comes, and let's say whenever any new person gives us information about whether they love movies, whether they love cartoons, and what's their age, can we predict whether that person will love Batman or not? This is the problem which we are trying to solve. Based on these three answers, whether they love movies, whether they love cartoons, and what's their age, can we accurately predict whether that new person will love Batman or they won't love Batman? In the previous lectures, we built this classification tree from scratch. So this turns out to be the optimal classification tree for training, where the first question we ask is to any person is, hey, do you love watching cartoons? If no, then we can confidently say that they don't love Batman. So that's the no side. If they say yes, they do love watching cartoons, then we ask their age. If the age is less than 12.5, we can confidently say that they do not love Batman. If their age is greater than 12.5, which means if they are in this branch, we can confidently say that they do love Batman. You can check this decision tree and whether it makes sense for the training data. Let me take the first data set. So first we ask whether they love cartoons. So this person says yes, great. So we go into this branch. Then we look at their age. Age is 70, which is greater than 12.5. So we look at this branch. So we'll predict that the person loves Batman. And indeed, oh sorry, the age was 7 over here. So let me erase this. So the age was 7 over here, not 70. So let's see again. So this first person, they loves cartoons, yes. So we are in this branch. Then their age is 7, which is less than 12.5, and then we can say that they don't love Batman. That's our decision tree prediction. And if you look at the true data, we will see that indeed this person does not love Batman. And if you validate this tree, you will see that for all the seven people in the training data set, it actually gives 100% accuracy. So if you take this decision tree and if you actually look at the training accuracy of this tree, you will see that the training accuracy of this decision tree is 100%. But today's lecture is not about training accuracy. It's more about testing and generalization. Let me explain that further. So this decision tree, as I mentioned, has 100% accuracy on the training data. But now let's look at some testing data examples. So let's say we have three people in the testing data, and let me mark them with a rectangle. This is my testing data over here. I have person 1, I have person 2, and I have person 3. So let's say you have built this decision tree, right? So someone comes over to you and says that, hey, can I test your decision tree on three new people? Then you say that, yeah, I've built this decision tree and I think it will work. So let's see. Uh, so let's see for person 1. They do love movies, they do love cartoons, and their age is 6. So let's see what our tree will predict. So first we check whether they love cartoons. So that's yes. So we go in this branch over here. Then we see their age, and their age is 12 point less than 12.5. So we go in this branch. So we'll predict that the person actually does not love watching Batman. So our prediction is that no, they do not love watching Batman for the first person. Let's look at it for the second person. Let's look at the loves cartoons. The answer is yes. So we again move in this branch over here. Let's look at the age. The age is again 7. So we again move in this branch. And so our prediction of the decision tree will be that no, they will not love Batman. So even for the second person, the prediction is no, they will not love Batman. Now let's look at the third person. The third person does not love cartoons. So we are directly in this branch. So our prediction will be that no, they don't love Batman. So for all of these three people, what our decision tree will do is that the decision tree will predict that neither of these three people actually loves Batman. And we give our answers to the person who asked us to test the decision tree. And now let us check our decision tree predictions. So for the first person, they actually did love Batman, and our prediction is no. So it was wrong. It's a wrong prediction. For the second person, they also loved Batman, but our prediction was no. Another wrong prediction. And if you look at it for the third person, the person did not love Batman, and our prediction was no. So this was a correct prediction. So if you see, out of the three predictions which we made, we got two predictions wrong and we got only one prediction correct. So two-thirds of our predictions, which means that 66% of our predictions were actually completely wrong. Um, so why is this the case? In fact, our training accuracy, as we saw over here, was 100%. So why is our testing accuracy only 33%? 66% of our predictions are wrong, which means only 33% of the predictions are correct. What causes this much decrease in the testing accuracy? So let us try to think about this. Um, if you analyze our optimized decision tree, you will see that if the most of the errors lie in this branch, right? So for the first two people, these two people, person one and person two, they loved cartoons and their age was less than 12.5. So we were in this branch. They loved cartoons, but their age was less than 12.5. We were in this branch. So something is not right in this branch. And let's try to figure out what that is. Okay, so if you go to this branch again in this decision tree, you will see that we can say that if you are in this branch, the person does not love Batman, but we have only one of the training data here. There is only one person here. So based on only one person in our training data, we have made this entire branch. There are three people here and there are three people here. So at least we have more number of people in these two leaves to make the prediction, right? But in this leaf right over here, which is loves cartoons, yes, and age less than 12.5 years, there is only one person over here. This is a big problem because based on just one person in the training data, we cannot make a decision tree. And in fact, we have seen that it's that place where we get most of the errors. These two people, person one and person two, belong to this branch over here, and they came to this leaf, but the answer was wrong for those people because we have designed this leaf and the answer of this leaf based on just one person's data. And this is the problem of overfitting. So basically, that person's data just might be noise, right? Just based on one data, we cannot construct a whole new branch here. We might be doing well on the training data, but due to overfitting, we are not doing very well on the testing data at all. And the main purpose of any machine learning model, as we have seen before multiple times, is not just to do well on the training data, but also to generalize well and to do well on the testing data as well. So the problem is that we need to avoid this overfitting, right? Just because one person says that they love cartoon and their age is less than 12.5 and they don't love Batman, we cannot say that for all people who love cartoon and whose age is less than 12.5, these people will also not love Batman. That's not good generalization. So we need to avoid this. So we need to avoid overfitting. So one way to avoid overfitting is to just start reducing the number of leaves. So currently we have three leaves here, right? This is leaf number one, this is leaf number two right here, and this is leaf number three. One way to really avoid or reduce overfitting is to reduce the tree length itself, to reduce the number of leaves in the tree. So this is the technique which helps us to prevent overfitting if we reduce the number of leaves. And reducing the number of leaves in a tree is actually called as pruning. It's very important for you to understand this terminology. This is where the name pruning comes from. Reducing the number of leaves in a tree is called as pruning. Pruning is that technique which can really help a lot in preventing overfitting. And in today's lecture, we are going to see how we are going to write down everything on the whiteboard so you'll understand everything from scratch. So this is the tree number one which we have. This is our optimized tree which we are looking at right now. So this is called as tree number one. I am also denoting this by number one here. Here you can see the number of leaves. There are three leaves in this tree. Now let us look at some pruned trees, which means let us look at some trees which have less number of leaves. So this is my tree number two. In tree number two, I'm just going to ask one question at the start. Loves cartoons? Yes. If yes, I'm going to say they love Batman. If no, I'm going to say they do not love Batman. That's it. This is my tree number two. So here you can see the number of leaves. There are two leaves in this tree. So this is a pruned tree, right? Tree number two is pruned because we have reduced the number of leaves. And now let's look at tree number three. Tree number three has only one leaf, which is that no matter what data which we have, we are going to say that everyone loves Batman. That is tree number three. Uh, okay, so here I'm going to say three, and I'm going to say this has only one leaf. So tree number two and tree number three are pruned trees, which means they have less number of leaves. The main question which we are going to ask is that, okay, we know that tree number one does the best performance on the training, right? If you evaluate tree number two and tree number three on the training data, they will give many errors. But the real question which we are going to ask today is that which of the above three trees is better for generalization, or how to select which of the above three trees will do better on the test data which we have not seen before. So let's get started with this question. To answer this question, first we need to understand a metric which is called as tree score. So what we will be doing is that we will define this new metric called tree score, and we will be evaluating this metric for all of these three different trees. And you will see in a moment why we are doing this. If you're familiar with regression, the tree score is very similar to the regularization in regression, and you will see why. So here is how the tree score is defined for classification decision trees. Tree score is the summation of the total Gini impurity plus alpha times number of leaves. This alpha is called pruning. It can be called pruning parameter. It's a hyperparameter which we have to determine, and I'll show you how to determine this. But basically, if you have a classification tree, the tree score is the summation of the total gene impurity plus alpha times the number of leaves. So here we are penalizing the number of leaves. More the number of leaves, we are going to say the tree score is going to be very high. So in general, our goal will be to reduce or minimize the tree score as much as possible. And do you see the similarity with regularization? In least square regression, the loss was the sum of the least square loss plus lambda times modulus of theta whole square, right? This modulus of theta whole square was the summation of the absolute summation of the parameters. So this was introduced to make the model as simple as possible. So you can think of this pruning parameter term alpha into number of leaves as being introduced to make the model as simple as possible. Because if the model becomes complex, the number of leaves are going to increase, which means our tree score is going to increase, and we do not want that. We want the tree score to be as low as possible. So the first intuition which I want you all to remember is that pruning is very similar to regularization in regression problems. Our main goal is to reduce the complexity of the decision tree so that it does better on samples which it has not seen before. Or put in other words, its generalization performance improves. This is the same thing why regularization is introduced in regression, to make sure that the model is not unnecessarily complex and it's not overfitting. So now what we are going to do is that after introducing the concept of tree score, we are going to find the tree score for all the three trees, tree 1, tree 2 and tree 3. So we define these trees over here, right? Tree 1 has 3 leaves, tree 2 has 2 leaves and tree 3 has only 1 leaf. We are now going to find the tree score for all of these leaves. So the first component here is the total Gini impurity. So let's compute that. So first we are only going to look at tree number 1. So this is the tree number 1. This is the optimized decision tree which gives 100% training accuracy. You can check that based on the training data. So to calculate the total Gini impurity, what we have to do is that we have to look at the nodes. So this is node number 1, this is node number 2 and this is node number 3, and we have to add the Gini impurity for each of the nodes. So let's look at node number 1 first. Node number 1 is basically loves cartoons and age is less than 12. So loves cartoons and age is less than 12. So we are going to look at the number of people who satisfy this and see whether they love Batman or not. So loves cartoon equal to yes and age is less than 12.5. So let's see. So loves cartoon equal to yes and age is less than 12.5. I have only one person and that person does not love Batman. So one no and zero yes. So this is what we are going to write here. So for node 1, yes is equal to 0 and no equal to 1. So the Gini impurity is going to be 1 minus probability of yes whole square plus probability of no whole square, which is 1 minus 1, which is equal to 0. If you are not familiar with Gini impurity, it is just 1 minus probability of yes square plus probability of no square. And we have a separate lecture entirely devoted to this concept. So please feel free to watch that lecture to understand the concept of Gini impurity. So the Gini impurity for node number 1 is equal to 0. Now let's see for node number 2. Node number 2 is basically loves cartoons and age is actually greater than 12.5. This should be 12.5. So node number 2 is loves cartoons and age greater than 12.5. So let's see in the data set. In the data set, loves cartoons, yes, and age greater than 12.5. So these are these three people over here. And we can see that those are 3 yeses and 0 nos. So that's what we are going to write over here. 3 yeses and 0 nos. So the Gini impurity is 1 minus probability of yes square plus probability of no square, which is 1 minus 1, which is equal to 0. So the Gini impurity for node number 2 is 0. Now let's look at node number 3. Node number 3 is basically just the people who say no to the question of whether they love cartoons. So let's look at those people. So it's this person here, this person here, and this person. And to all these three people, the answer to loves Batman is no. So 3 no and 0 yes. So for node number 3, I have 3 no and 0 yes. So the Gini impurity is 1 minus 0 square plus 1 square, which is equal to 0. So we see that for the first tree, the Gini impurity for all the nodes is 0. It's a fully pure tree since it has no misclassifications on the training data set. So to calculate the total Gini impurity, we will take a weighted sum. For the node 1, we have one person who belongs to node 1, right? In node number 2, we have a total of 3 people. And in node number 3, we have a total of 3 people. So the Gini impurity is 1 by 7 into Gini impurity of node 1 plus 3 by 7 into Gini impurity of node 2 plus 3 by 7 into Gini impurity of node 3. And since the Gini impurity of node 1, 2 and 3 is anyway equal to 0, the total Gini impurity of tree 1 is going to be equal to 0. The number of leaves in this tree are 1 2, and 3. So there are 3 leaves. So the tree score is the sum of the total Gini impurity plus alpha into the number of leaves. So it's 0 plus 3 into alpha, which is 3 alpha. That's the tree score for tree number 1. Now let's look at tree number 2. Tree number 2 is very simple. Loves cartoons. Yes. If the person says yes to loves cartoon, we are going to say they love Batman. If the person says no to love cartoon, we are going to say they do not love Batman. Great. So let's look at node number 1, which is basically loves cartoon equal to yes. So let's look at the data set again. I'm first going to erase some of these things over here so that it will be easy to uh, okay. So in the node number 1, we have the people who have answered yes to loves cartoon. So it's 1, 2, 3, 4. These 4 people. And let's look at love Batman. So love Batman, there is 1 no and there is 3 yeses. So there will be 1 no and 3 yes. That is exactly what I'm going to write here. For node 1, yes is equal to 3 and no is equal to 1. So the Gini impurity is 1 minus probability of yes the whole square, which is 3 by 4 square, plus probability of no square, which is 1 by 4 square. So the Gini impurity of node 1 comes to be 0.375. Remember, it's not 0 because it has a mixture of classes. It has a mixture of yeses and nos. Whereas in the previous tree, all the nodes were fully pure. They did not have a mixture. Now let's look at node number 2. Node number 2 is all those people who don't love cartoons. So it is this person, these 3, and we can say that they do not love Batman. So this is going to be pure node, 3 no's and 1 yes. So in node number 2, I have 3 no's and 0 yes. It's a pure node. So the Gini impurity is 1 minus 0 square plus 1 square, which is equal to 0. Now in node number 1, the total people who are there are 3 plus 1 equal to 4 because 4 people love cartoon. And in node number 2, the number of people are 0 plus 3, which is 3 because 3 people say they don't love cartoon. So the total Gini impurity is 4 by 7, 4 by 7 into 0.375 plus 3 by 7 into 0, which is 0.214. So for tree 2, the total Gini impurity is 0.214 and the number of leaves in tree number 2 are equal to 2. So the tree score is equal to the total Gini impurity plus number of leaves into alpha, which is 0.214 plus 2 alpha. So the tree score for tree number 2 is equal to 0.214 plus 2 alpha. Great. Now we actually move to tree number 3. Tree number 3 is just we are going to say everyone loves Batman. So now let's look at the data and see how many do love Batman and how many do not love Batman. So if we look at the data set, if you look at the orange ones, we can see that there are 4 people who don't love Batman and 3 people say yes. So in tree number 3, there is just going to be one node and 4 people say no and 3 people say yes. So the Gini impurity is 1 minus the probability of yes whole square, which is 1 minus 3 by 7 whole square plus the probability of no whole square, which is plus 4 by 7 whole square. So this calculation turns out to be 0.489. So you will see that for tree number 2 and tree number 3, the Gini impurity is not 0, right? Which means that these trees do make mistakes on the training data. So for tree number 3, let's calculate the tree score now. The total Gini impurity is 0.489 because there was only one node. So we don't need to take the weighted average. And the number of leaves is equal to 1. So the tree score is equal to the total Gini impurity plus the number of leaves into alpha. So number of leaves is equal to 1. So the tree score is equal to 0.489 plus alpha. So that is the tree score for tree number 3. So now if you put all of this together, if you look at tree number 1, tree number 2 and tree number 3, let's write down the tree scores for each of these trees. For tree number 1, the tree score is equal to 3 alpha. For tree number 2, the tree score is equal to 0.214 plus 2 alpha. And for tree number 3, the tree score is 0.489 plus alpha. So if you look at the two components, the Gini impurity component is the smallest for tree 1, which is 0. Gini impurity component is the largest for tree 3, which is 0.489. But if you look at the second component, which is the number of leaves, it's the opposite. The number of leaves are 3, which is the maximum for tree number 1, but the number of leaves are only 1 for tree number 3, which is the minimum. So these two terms are in opposing directions. The Gini impurity decreases as we go from left to right. So the Gini impurity, I'm going to say, decreases as we go from left to right. But now let me plot this in a different color. Actually, the Gini impurity increases as we go from left to right, because for tree number 1 the Gini impurity is the lowest. So the Gini impurity actually the Gini impurity increases as we go from left to right. Uh, but let me plot this with a different thing. As we go from left to right, the number of leaves, we write this again. So the number of leaves actually decrease as we go from left to right. So these two effects are in opposite directions. Please note that. Hence, we cannot just say that because tree 3 has a higher Gini impurity, its tree score is going to be higher. Note that its leaves are also lower. So that pulls the tree score in the opposing direction. Okay. Now, let us look at these three mathematical values: 3 alpha, 0.214 plus 2 alpha, and 0.489 plus alpha. And let us compare these tree scores now with each other. Ideally, we want to see at what value of alpha does tree 1 has the lowest tree score, at what value of alpha does tree 2 have the lowest tree score, and at what value of alpha does tree 3 have the lowest tree score. When you do the mathematical computations, which is very simple, you will see that if alpha lies between 0 and 0.214, then tree 1 has the smallest tree score. Whereas if alpha lies between 0.214 to 0.275, tree 2 has the smallest tree score. But if alpha is greater than 0.275, then we see that tree 3 essentially has the smallest score. Uh, so if you see, the important values of alpha are 0, 0.214, and 0.275. We can say that at these transition values of alpha, the tree becomes one depth shorter, because if the alpha value is between these, the best tree which will be chosen is the largest one. If the alpha value is between these two, the tree 2 will be chosen, and if alpha value is the highest, the tree 3 will be chosen. So now let us actually do one thing. Let us do the testing for these three trees which we have constructed, and let us do this testing for the person 1, the person 2, and the person 3. So remember that the person 1, person 2, and person 3 we had already seen before, and we had seen that the tree which we constructed had only 33% accuracy. It got two-thirds of the predictions wrong. Now let's see what these other smaller trees are doing. Okay, so this was the testing data set. Now let's look at tree number 1. So tree number 1 we had already evaluated before. It's the optimized tree, which looks like this. So it has two wrong and one correct. So the test accuracy is 33%. Now let's look at tree number 2. Tree number 2, what it says is that if the person loves cartoons, they loves Batman. If they don't love cartoon, they do not love Batman. So let's look at the person 1, 2, and 3. So for person 1, they loves cartoon. So our tree number 2 will say that they do love Batman. Person 2 also loves cartoons. So our tree number 2 will say that they do love Batman. Person 3 does not love cartoon. So we are going to say that they don't love Batman. And if you compare this with the actual answers, you will see that all of them are correct. So you will see that tree number 2 has all three correct. And hence the test accuracy for tree number 2 is actually 100%. And when will the algorithm choose tree number 2? When alpha lies between 0.214 to 0.275. When will tree number 1 be chosen? When alpha lies between 0 to 0.214. Now let's look at tree number 3. So if you look at tree number 3, it's basically saying to everyone that they love Batman, right? So let's look at the test data. So we can see that two people do indeed love Batman and one does not love Batman. So we have one wrong and two correct. So the testing accuracy is 66% for the third tree. So we can see that tree number 1, although it has the highest training accuracy, it has actually the lowest testing or generalization accuracy among all of these three trees. In fact, it has a testing accuracy of only 0.33%, whereas tree number 2 and tree number 3 have better testing accuracies. In the example which we have chosen, tree number 2 has the maximum test accuracy, and hence the optimum value of alpha which will be chosen in this case is lying between 0.214 to 0.275. So this example clearly illustrates in a very practical manner that when you look at decision trees, don't just evaluate training accuracy. The tree might be very big and the training accuracy would be very small, and you might think that you have done a great job, but always make sure to evaluate the testing accuracy. Smaller trees may do a worse job on the training data, but they can actually do a better job on the generalization data, as we have already seen here, or better job on the test data, as we have seen here. So for this problem which we have chosen, the best value of alpha lies between 0.214 and 0.275. That's the optimal value of alpha. So in practice, what we have shown here in testing is actually performed through k-fold cross validation. So in practice, what is done is that first we have uh, these important breaks of alpha, right, or these transition values of alpha. In practice, what is done is that first you construct the full tree, then you get these transition values of alpha, then you do a k-fold cross validation, similar to how we have evaluated for the testing data here, and based on the k-fold cross validation you choose the optimal value of alpha, and then you proceed with the testing. So I have not shown the validation data set here, but to select the value of alpha we actually use the k-fold cross validation. So this is how overfitting is avoided in decision trees through the method of pruning. This particular method of pruning, where we introduce this thing called tree score, is called as cost complexity pruning, or CCP. And whenever many people run decision tree algorithms, they directly use the decision tree framework through scikit-learn, etc. And they have seen the word CCP, but they never understand how CCP actually works or what CCP really means. In this lecture, I wanted to give you that understanding in a very hands-on and practical manner. So this is cost complexity pruning, and the way it is implemented in practice is that there are essentially four steps. First, you get started with the full tree. That's the step number one. Then what you do is that you find alpha values for each level of pruning, which means that level of pruning means in this case the zeroth level of pruning is tree 1. The first level of pruning is tree 2. The second level of pruning is tree 3. So the trees get shorter and shorter and shorter. So you find the alpha values for each level of pruning. So in this case, the alpha values are 0, 0.214 and 0.275. So you find these alpha values for each level of pruning. So if you are familiar about Python coding for decision trees, you may have come across this term CCP alpha. CCP alphas actually consist of these alphas, um, which are the alpha values at each level of pruning. But we don't have to stop here. We have to find the ideal value of alpha, and that is done through cross validation. So it's always very important to divide the training data set into k-fold cross validation to find the best value of alpha. And then finally we perform on the testing data set based on the value of alpha which has been chosen. This is how overfitting is avoided in decision trees. So it's once you understand the method, it's actually quite simple to understand. But I have seen very few videos in which this is actually done in practice. StatsQuest has a very good video where they show pruning for regression trees but not for classification trees. If you are looking at regression trees and if you want to implement pruning, the only thing which changes is that when you calculate the tree score, instead of looking at the total Gini impurity, what you actually look for is the least square summation. That's the only or the least square sum. That's the only thing which changes. Everything else remains the same. Don't worry, I'll create a separate lecture for that so that you can understand how the tree score is calculated for regression trees. Okay, so one thing which I want to show you is that when you actually implement this in Python, it will look something like this. This CCP means cost complexity pruning. So whenever you calculate or you get the full decision tree, you implement this cost complexity pruning, and then you store the alphas. So these are the transition point alphas which I mentioned, CCP alphas. These are point 0, point 214, point 275 which I mentioned. You store these and then you compute the k-fold cross validation. So here you can see the cross validation has been performed. Actually, I think it has been performed over here. Yeah, the cross validation has been performed over here, and then you select the best alpha. So, for example, if the cross validation looks something like this, you can see the accuracy plotted for different values of alpha. So, this point here, this alpha gives the highest accuracy. So this has to be chosen for testing or generalization. This is how it actually works in practice. No problem. We'll come to this when we come to the Python coding part. But it was very important to explain this concept of pruning. In the next lecture, we are actually going to look at Python coding, where we are going to build an entire classification tree from scratch, and we are also going to perform the pruning operation over there. Uh, that is the reason I wanted to take this lecture before the next one. Also, please keep in mind that in all of this decision tree from scratch series, as you can see, I try to explain everything from scratch as much as possible without assuming anything. And this is the learning approach which you should also follow when you understand machine learning algorithms. Instead of directly going to complicated libraries and implementing the libraries, it's always better to understand everything from scratch, which is the philosophy of this lecture series. So, thank you so much, everyone, and I look forward to seeing you in the next lecture.